We're looking at chi-square, which is a statistical test. This is the Greek letter chi. We don't use that sound in English very much, so we tend to call it the chi-square. And we use it as a symbol to represent the goodness of fit between two sets of data. So we're testing that goodness of fit today. That's what we're looking at. So I'm going to just quickly sketch a couple of sets of data for us here. I'm going to stick with our standard example about height and shoe size. So this is the height of the people in the space. Most people tend to fall in the middle when it comes to height. It's a normal distribution. Sorry, this isn't a very good normal curve, but you get the idea. Most people are in the middle. Few people are short, a few people are tall. Then if we ask, well, our other example was shoe size, and we're asking, is there a relationship, is there an association between height and shoe size? And again, most people tend to have ordinary size feet, and you get very few big feet and very few little feet. And it's a bit tighter. This one's, we call this a leptokurtic or tight curve. It's not really very normal at all anymore. And there are differences between the curve and the height curve. And those differences there, what we want to know is, are those differences that we can see down to just the ordinary variations we'd expect in any variable? Or can they be attributed to the fact that we've measured different, genuinely different things? Now it is generally true, the taller you are, the bigger your feet. So if you measure somebody's shoe size or foot size, in a way you kind of have measured their height, usually. What we want to know is that association strong enough for us to treat the one as being roughly the same as the other, the variations in one as being roughly the same as the variations in the other? That's what the chi-square is for. For contrast, think about an alternate example, okay? So this is the other group of people that we might think of when we're doing height and shoe size. So these are the clowns, yeah? So most clowns don't fall in the same pattern of variation. In fact, you wind up with something that we call a bimodal distribution. That's a very poorly drawn one, but you get the general idea. There's two modes. There's two sets of data, two humps in the graph, where, you know, that's where the most people are and the most people. Mode is the most people. But that's their heights then. So we're already looking at something that's very different. And this is their shoe size. Of course, if you look at clown shoe size, clowns always have big feet. So the majority of people are like that. Now we can see that the variations between the two graphs are really marked, much, much bigger variation there. And so we would calculate a chi-square statistic to tell us what that variation actually looked like. And that's basically what we're doing today, looking at how we would do that calculation. So when do we use a chi-square? When we want to know the likelihood that two samples belong to the same population or to different populations. That likelihood, that percentage, is called an alpha value, an alpha probability, and there are other resources that help you to understand that elsewhere. We do this by comparing one of the groups to the other by looking at their relevant shared features. So think about, here's some ants, okay? We want to know, are these ants sufficiently similar to these ants for us to conclude that they came from the same colony? Well, first inspection we might say they're very similar colouring, similar size, similar shape. Yeah, they probably did. Of course, size, shape and colouring are relevant to species, but they may not be relevant to colony. You know, you could look at the very, very similar to somebody else who came from a very different part of the world and never met before, so they might not come from the same colony at all. We'd have to look at diet or the soil type that they lived in or something like that to work out whether they came from the same colony. Here's another example for you, one that's much closer to my heart. So there's the beer. Is this pint sufficiently similar to this pint for us to be able to conclude that they come from the same barrel? Well, the relevant comparator this time is colour. This is darker and redder, and this is paler and yellower. And I don't think they came from the same barrel because they're too different in terms of their relevant comparator. So I would say they probably came from separate barrels. In fact, I'd say that came from a bitter barrel and that probably came from a lager barrel. Now, our hypothesis is always going to be, we start out by saying the two things come from the same basic population. And we think that idea is wrong. But we're going to test it anyway because as scientists, we test the hypothesis to prove that it is wrong. We do test our hypothesis to destruction. And we do that because of something called the problem of induction. If I say all the swans in the world are white, I can get 20 swans and that's a bit of evidence to support that proposition. Or I could get 200 and that's more. I could get 2 million and that's loads. But I can never have all the swans that have ever existed in one space and show that they're all white. I can't complete the observational set for that proposition. And if somebody comes along with just one black swan, the hypothesis is out the window. So disproving hypotheses is always a more efficient thing to do than proving them. So what we do is we assert the hypothesis that is the opposite of what we believe and then disprove it. And on that basis we show we've got better evidence for what we actually think is the case. When we do this, our samples can be anything that we can collect counting data about. So we could count the number of right-handed people there were in a room and the number of people over 6 feet tall. We could count the number of children achieving test scores in a particular range from 2 different school classes. So how many came from this class, how many came from the other one. We could count the number of employees taking 5 or more days sick leave and then the number of employees under the age of 25. Each time we'd be asking, is there an association, is there a link between these two samples? So is there a link between being tall and right-handed? Or is there a link between achieving a certain test score and being in one class or another? Or is there a link between being relatively young and taking time off work ill? Besides it having to be being used counting data like that, what we're doing is we have to meet certain criteria, characteristics of the data. So the data has to be in tally form. That means that it's going to be, we're counting frequencies of a certain category. So if we're thinking about the Christmas tree example, Christmas lights example, we go around the neighbourhood and we count how many houses have Christmas lights outside. They either do or they don't. So we're just counting a categorical difference. And that helps us with the second criteria, which is that any data has to only appear in our counting just once. So, this house only gets counted once. It either has got Christmas tree lights or it hasn't. Can't be related. To look at related data, do think about this example. So if we've got people taking class tests and we looked at the scores from the midterms and then the finals, that data is related because presumably we'd be able to show that person 1 had got an F in their midterms and an A+ in their finals. That could happen, couldn't it? So you could have the same person being counted twice in the data. Now that can't happen if you're going to use a chi-square. Chi-square has to work with independent data. You can get tests of goodness of fit for related data, it's just it mustn't be a chi-square, it's a different kind of test. Finally, there's a technical thing that we have to meet, a technical criterion, which is about something called the expected value. Now an expected value is a statistical feature. I'll show you how to calculate that in a minute or two. And a contingency table is the way we set out the data in a chi-square analysis. Now, what the requirement is that the expected value in any element, any cell of the contingency table must be 5 or more. Now, don't worry if that doesn't make much sense, it doesn't matter. What I wanted to do is point it out because it's a requirement that you see in a lot of statistics books, but there are many statisticians who would say you don't need to worry about that. It's not that important. So it is a requirement that's set out in traditional chi-square analyses, but there are many statisticians who would say it's not that big a deal if we don't actually meet that criteria. If, however, we can show that we've met all 3 of those criteria, everything's good, we can go on and do a chi-square analysis of the data. Now, Picasso's Weeping Woman, if it all seems a bit abstract, we need some concrete examples here, which is where we're going next.